All right, welcome to The Explainer. Today, we are tackling one of the biggest, most ambitious scientific quests in all of human history, nuclear fusion. We're going to talk about what it is, why it's basically the ultimate energy prize, and how close are we, really, to bottling the power of a star right here on our planet.
Okay, so let's just dive right in. At its heart, fusion is surprisingly simple. It's about taking tiny particles, atomic nuclei, and smashing them together so hard they become one. Now here's the magic. The new particle you create is actually a little bit lighter than the two that went into it. That missing bit of mass doesn't just disappear. It converts into a huge blast of pure energy. Yep, that's Einstein's famous EMC² in action. Now, you've probably heard of nuclear fission, right? That's what our current nuclear power plants do. But fusion is its complete opposite. Fission is all about taking a great big, heavy atom, like uranium, and splitting it apart. Fusion? Well, fusion is about taking really small, light things, like hydrogen, and building them up. So one is breaking things down, the other is building them up. Totally different games.
And get this isn't some sci-fi theory. It is happening right now on a scale that is just impossible to wrap your head around. Fusion is literally the reason stars shine. I mean, think about our sun. Every single second, it's fusing about 620 million metric tons of hydrogen. That's the engine that gives us all the light and heat that makes life on this planet even possible.
So why on earth are we trying to recreate that cosmic engine down here? Well, the answer is pretty simple. Because if we can crack this, we unlock a source of clean energy that could power our civilization pretty much forever.
And the list of benefits? I mean, it reads like a dream. The fuel? An isotope of hydrogen called deuterium, which you can get from plain old seawater. There's enough in the oceans to last us for millions of years. It produces zero greenhouse gases, and maybe the best part, it's incredibly safe. If anything goes wrong in a fusion reactor, the reaction just stops. No chain reaction, no meltdown, no long-lived nasty waste. It just fizzles out.
And the power. Oh, the power. A single tiny fusion reaction unleashes an absolutely massive amount of energy. To give you some perspective, gram for gram, it's millions of times more powerful than any chemical reaction we use today, like burning coal, oil, or gas. It's just on another level.
Okay, so if it's this amazing, this perfect, what's the catch? Why isn't every city powered by fusion right now? Well, the answer is that trying to build a star on Earth is, and I'm not exaggerating, monumentally difficult.
You know, the sun makes this look so easy, but it's got a secret weapon that we just don't have: gravity. A mind-boggling, unimaginable amount of it. The sun's sheer mass just crushes those atoms together in its core. We can't do that. We have to find another way. So what's standing in our way?
It all boils down to one fundamental problem in physics, the Coulomb barrier. See, atomic nuclei are positively charged. And if you remember from science class, like charges repel. So trying to push two of them together is like trying to force the north poles of two super strong magnets to touch. They fight back with an incredible, invisible force.
So to overcome that force, you have to create conditions that are frankly insane. We're talking about temperatures hotter than the core of the sun, over 100 million degrees Celsius. At that temperature, matter isn't a solid, a liquid, or a gas anymore. It becomes a fourth state of matter, a superheated, electrically charged soup of particles called a plasma.
So, new problem. How in the world do you hold on to something that's over 100 million degrees hot? I mean, any physical container would just vaporize instantly. To solve this seemingly impossible puzzle, scientists are basically chasing two main ideas.
You can think of it as the magnetic bottle versus the hammer blow. The magnetic bottle approach is about finesse, using powerful, invisible forces to gently contain the plasma. The hammer blow is all about brute force, hitting the fuel so hard and so fast it doesn't have a choice but to fuse. With magnetic confinement, you create your super hot plasma, and then you trap it inside an invisible cage made of incredibly strong magnetic fields. The most popular design for this is called a tokamak. It's basically a giant magnetic donut that forces the plasma to race around in a circle, never touching the walls.
Inertial confinement, on the other hand, is like a tiny, perfectly controlled explosion. You take a little pellet of fuel, smaller than a peppercorn, then you blast it from every direction at once with hundreds of the most powerful lasers on the planet. The outer layer of the pellet vaporizes, creating a rocket-like implosion that crushes the fuel inside, creating fusion conditions for just a split second. Now, this decades-long quest isn't just theory anymore. We are finally seeing real, measurable progress. I mean, for years it was slow going, but just in the last few years, we've hit some historic milestones that have everyone thinking we might actually be getting close.
If you look at this timeline, you can see the story unfolding. It was a slow burn for decades, from the first tiny sparks in the 50s to bigger experiments in the 90s. But then, boom. The last few years have been packed with genuine, game-changing breakthroughs on both of those paths we just talked about.
The big one came in 2022. This was the Holy Grail. The National Ignition Facility, using that hammer-blow laser approach, achieved what's called ignition. For the first time ever in a lab, they got more energy out of the fusion reaction than the energy they put in to start it. They put in about 2 megajoules of energy and got out over 3. That proved it could be done.
And then, just this year, in 2024, the magnetic bottle team had a huge win. The JET tokamak in the UK shattered the world record, producing 69 megajoules of energy in a single 5-second pulse. That's enough energy to power a house for a few hours, all from a pinch of fuel.
So, where does that leave us? We've had these incredible breakthroughs. Does that mean fusion power plants are right around the corner? Well, the next great challenge is taking these amazing experiments and figuring out how to scale them up into a real working power plant.
And for that, pretty much all eyes are on this gigantic project being built in France called ITER. ITER is going to be the biggest tokamak ever built, by far. It's important to know it's not actually a power plant. Think of it as the world's most complex and expensive test engine, designed to prove that we can get a whole lot more power out than we put in on a massive scale.
And what's really amazing about this is who's building it. This isn't one country's race to the finish line. It's one of the biggest scientific collaborations in human history. We're talking nations that are often rivals on the world stage, all pooling their money and their best scientists to solve this one enormous challenge together.
But here's the reality check. We have to be patient. While the promise is incredible, turning fusion into a commercial power source is still a long way off. This is a marathon, not a sprint. ITER itself has faced delays, and its biggest, most important experiments aren't even scheduled to start for more than a decade.
So here's where we stand. For a fleeting, brilliant moment, we have ignited a star on Earth. We have proven the physics works. But the challenge for the next generation of scientists and engineers is a different one. It's not just about creating that pulse of energy anymore. It's about moving from a brief flash to a steady, sustained burn. The question isn't just if we can light